Hello dears, here we will start Module 4 material. Module 4 material will be covered in 3 weeks as usual, where in week 11 we are going to discuss stability, and week 12 and 13 we will deal with root locus. We will start here with the stability of the control system. Of course, in stability we are going to consider always the system which linear time invariant system. The system which we are going to deal with is only linear time invariant system. We are going to keep in our mind that the response C of t equal to C force plus C natural. Remember, in the transient stability we mentioned this point. Always the output, the response, is coming as a result of two elements, the force response and the natural response. Now if I want to look from natural response perspective, let us define stability. So here he's saying a linear time invariant system is stable if the natural response approaches zero as time approaches infinity. That means you are going to reach to a point with the response where the exponential is not going to have effect on it. So you are going to get the system to the steady state. Once I get to the steady state, that means the system is stable. If you consider the next one, and again the linear time invariant system will be unstable if the bounded input result to unbounded output as it's approaching infinity, which means if this is the input and the output is not, you see it's having certain boundary, it's going to be within certain boundary. If the output comes without boundary, means keep increasing, we are going to assume that the system is not stable. And marginally stable is something in between. It's neither this nor that, which means the system going to oscillate. System going to oscillate around the certain point. So this is going to be the what is called marginally stable. Now, as I said, stable means bounded input will result in a bounded output, and unstable bounded input will yield to unbounded output. That's what we need to keep in our mind while dealing with stability. Stable system or unstable system, we will find that the poles all located on the left hand side of the S-plane. So if this is S-plane, the poles are going to be located on this side. None of the pole will be on the right hand side. In marginally stable, you will find that the poles will have, some of the poles will be on the imaginary axis. And unstable, you will find at least one pole on the right hand side. Maybe this on the right hand side, whatever on the left hand side, let us say these poles are on the left hand side. If one pole or more on the right hand side, that means the system is unstable. This is kind of indication for us, kind of method to tell us whether the system is stable or not stable. Let us proceed with the properties of stability, which will help us to know whether the system is stable or not stable. Now, if I look at the denominator of the closed loop transfer function, there is an indication of stability or not stability. If you notice in the previous slide, we mentioned that the indication will be through the location of pole. Also, this one is coming from the location of pole, but we are going to go direct to the characteristic equation, this equation, which is called characteristic equation. So if the sign of the denominator comes positive and negative, system is unstable. Like here we have positive, negative, positive, positive, positive. If one negative, if there is any change in the sign, means the system is unstable. Not only this, if we are missing any power in the denominator, as you see here, that means the system is unstable, which means here s to the power 4 and s to the power 2. There is no s to the power 3. So this is another indication showing that the system is unstable. Now let us say we have all of these things satisfied. Does it mean that the system is stable? This is satisfied, and the other elements before are satisfied. Does it mean that the system is stable? No, not sure. So after making or satisfying all of these conditions, we have to apply a theory to make sure that the system is stable. So whatever we mentioned earlier can prove that the system is unstable. But to prove that the system is stable, we need to apply certain methods. Before we go to the method, let us figure out the meaning of stability, or how can I get the stability from the system. Of course, when I have such a system, if I want to study its stability, let us get the characteristic equation. Remember that the characteristic equation is the denominator of the closed loop transfer function, 1 plus gh, which, as you see, is going to be this part. When we solve it, is going to be this value. So he simplify it or rearrange it, you are going to get this equation. As you see, it's third order equation. That means there are 3 poles available in this system. 3 poles available in the system. One will be at minus 2.6. The other will be at minus 0.16 minus J1.4. And the third will be at minus 0.16 plus J1.04. So here are the location. We are having one pole here, and the complex one here with this other complex will be here. If we try to plot this one, we are going to come out with this response. So if you notice, this is the input, and the output ultimately reach to bounded output, means it's going to oscillate within limited area. That's what we mean by bounded output. So from here we can say that this system is stable. Of course, if I keep in my mind the previous system, if anything else, means the system is unstable. Talking about the previous slide, if this is the input and the output get to be something like this, for example, you see, no bounded output. So this is showing that the system is unstable, just to keep in our mind. Let us come now to the criterion which will test the system stability without doing the method mentioned earlier, because I think it's not going to be practical to calculate the closed loop transfer function for any system given and get the pole with the pole location. Is going to be long process, especially if the system is higher order. For that, we are going to deal with this criterion, which is called Rourth-Hrwits Criterion, to decide whether on the system stability without doing this kind of calculation. That's one thing. And the other thing, even it can tell me the number of poles at each location, like the poles on the left hand side or right hand side. This is all can be done by Rourth-Hrwits criterion. How to do Rourth-Hrwits criterion? We are going to generate the Rourth-Hrwits table, then we will interpret it. You will see after a while that we are going to generate table, and then we will interpret the table. Here is the table which we are going to generate. So in generating the table, first of all, we are calculating the closed loop transfer function. From the closed loop transfer function, we have what is called, again, characteristic equation. From the characteristic equation, we are going to build the table. The table is to be done like this. If you notice here, we have the order is 4. This is fourth order equation. So I'm going to arrange the S starting from the highest order to S to the power 0. As you see here, S to the power 4, S to the power 3, S to the power 2, S to the power 1, and S to the power 0. Which means if this equation 10th order, we are going to start with 10 to the power S to the power 10, S to the power 9, S to the power 8, until S to the power 0. Okay, then after that, we are going to arrange the coefficient of the equation in the table as shown here. What do I mean? You see, coefficient of S4, it's going to come here. Coefficient of S3 will come here. So we are going to arrange this coefficient A4, A3, A2, A1, A0 in this style. A4, A3, then A2, then A1, then A0. Finish, then the remaining item in the table will be zeros. Now after that, we will find these elements in the table. We will find these elements. How to find them, we will see in the next slide. So to calculate this item, we are going to build this matrix, which to be taken as this column, first of all, minus of this column, and take this column. You see this column to be here, this column to be here. Divide them by A3, by this element. You will calculate B1. Now let us proceed. In the next item, when I want to do this one here, what is the changes? Everything will remain the same. I mean, this column will be the same, this item will be the same, except this column will be replaced by this column. Continue. When I go to the next one, you are going to find everything will be the same except this column will be replaced by this column, and so on. That's how we can do it. That's for this row. That's for this row. Now, how about this row? We are going to repeat the same thing, but we are going to keep this column with this column divided finally by, we will divide the whole thing by B1. So as you see here, minus A3B1, A3B1, A1B2, A1B2, divided by B1, all minus. That's going to give me C. So how about this one, this item? In this item, we will do the same thing, except this column will be replaced by this column. Following by, I mean, if I go to this item, it's going to be this column will be replaced by the column which coming from here, which 0, 0 anyway, and so on. That's how we can build the table. After building the table, of course, we will interpret it for stability. We will come to the interpretation after a while. Let us figure out how to make that Rourth-Hrwits table first of all. So in the steps, I think this is what I mentioned in the previous slide. So the steps, you can go through them. It's what I mentioned exactly in earlier slide. Let us look at this example, because by numbers things will be easier. If I have this system with the open loop transfer function given as you see here, and we need to make Rourth-Hrwits table for this system. To make Rourth-Hrwits table, we are going to calculate the closed loop transfer function. Closed loop transfer function means this value divided by 1 plus this value. I hope you understand, or you remember this is G of S. TS is equal to GS over 1 plus GS. Hopefully you remember this. Okay, so when we simplify the function to the minimum, that's what we are going to get. And the characteristic equation will be this part. Now, when you look at the order, you will find it's third order. That means we will start from S to the power 3, S to the power 2, S to the power 1, S to the power 0. And then we are going to place the coefficient of each S. So here 1, look here, 1, 10, 31, and 1030. 1, 10, 31, 1030. If for any reason you want to continue by zeros. The remaining will be zeros. Okay, now we will start building the table. Before we proceed in building the table or continue the other table items, just for a matter of simplicity, instead of dealing with high numbers, sometimes we can deal with smaller numbers. For that, or to simplify the table or simplify the calculation, he said you are allowed to divide or multiply any row in any number you like, but don't touch the sign. Don't play with the sign. That means you can multiply the row on any positive quantity. Like here, I will multiply this row by 1 over 10. So if I multiply 10 into 1 over 10, it's going to be 1. 1030 into 1 over 10 equal to 1 and 3. And here it's going to be 0. Or divide by 10. It's up to you how you want to call it. So now we are going to deal with these numbers. So we replace 10 by 1, 1030 by 103, 0 by 0. Now we can proceed. How to get the rest of the table? Notice that this column, let me put it with red color, this column is going to come here. And this column will come here. Divided by this item will come here. This is the idea. Of course, with minus. Don't forget the minus. and calculate it as you are solving matrix. Like you are going to say, to evaluate this quantity, it's equal to minus, and let me write it here, minus 1 into 103 minus multiplied into all 1 into 103 minus 31 into 1 all divided by 1. That's how you can deal with it. So when you solve it, you are going to find that it's minus 72. I'm repeating. To solve the value 1 into 103 minus 31 into 1 divided by 1 and all minus, that's going to end up with minus 72. Same thing for this part. For when I come to this side, notice that the only element will change is this column. We replace it by this column. This column will be replaced by this column. Other than this, don't change anything. And solve it. Of course, 1 into 0 minus 1 into 0 over 1 equal to 0. So the rest will be zeros. That's how we can get this row. Now let us go to the following row. In the following row, we are going to do the same thing, but keeping in our mind, we are going to eliminate this row. This row is not needed anymore for the table. So I'm going to take this column with this column divided by this item, divided by this item, all minus. So notice this column and this is the other column, all minus, all divided by minus 72. When we solve it, and it's to be solved like this, 1 into 0 minus 103 into minus 72, all minus, divide by minus 72. When you calculate it, it's equal to 103. So that's how we can calculate the table, and by this way we can get Rourth-Hrwits table ready for interpretation. In the interpretation of the Rourth-Hrwits table, all what we will look at is the first column, only the first column. We have the table, whatever table, like the table in the previous slide, is to the power 3, is to the power 2, is to the power 1, is to the power 0, and we have the rest of the table, whatever. What we are going to look at is only the first column, only this column, and we are going to look only at the sign, whether positive or negative. We are not going to look at the values. We don't need the values. We need only the sign. So according to the rule, he's saying any change in sign is equal to the number of poles on the right hand side. What do we mean by this? If the sign here is positive, negative, positive, positive. So you will find here that the sign is start by positive, then it changed to negative. This is the first change. Change to positive, the second change. So there are two changes in sign. Then after that, no changes, because positive to positive. So if we have two changes in sign, this is an indication of the number of poles located at the right hand side. So if the poles or the changes in sign are 2, that means there are 2 poles on the right hand side. As we agreed earlier, 1 pole on the right hand side is enough to make the system unstable. So this is an indication of a system not stable. But remember, I am not doing the Rourth-Hrwits stability to check whether the system is stable or not. Not only this is not the only reason for that. We need to count the number of poles at each location. This may help us in the design. Number of poles in the right hand side, number of poles on the left hand side, and number of poles on J omega axis. That's what you are going to see in the example as we are going through the material. Special case. There are special cases you are going to meet while dealing with the Rourth-Hrwits table, which if you are not taking action with these cases, you are going to face problem in continuing the table. Let us check these cases.